The year was 1964. The Cold War was a deep, unshakable chill. While the world looked at missiles and borders, a Soviet physicist named Igor Novikov was looking at the stars. Or, more accurately, he was looking at the math that described the stars. He was working with the equations of Albert Einstein, the same equations that predicted black holes. Everyone was getting used to the idea of black holes. These were places where gravity was so strong, nothing could get out. Not even light. They were cosmic drains, the ultimate dead ends. But Novikov saw something else hidden in the math. In physics, equations often work just as well forwards as they do backwards. If you have an equation that describes a ball falling, you can run it in reverse to describe a ball being thrown up. Novikov applied this simple idea to the math of a black hole. He ran the equations backwards. Instead of a region of space that only pulls things in, the math described a region of space that could only push things out. It was a place where nothing could enter. He called it a white hole. It was the time-reversed opposite of a black hole. Matter and energy would spew out of it violently, not in a slow leak, but in a single explosive burst. The idea was born not from observation, but from pure mathematical symmetry. It was a ghost in the machine of general relativity. For Novikov, it was a logical possibility, a what if. But for cosmology, it was the start of a deep and strange puzzle. A puzzle that, decades later, is even weirder than the one about black holes. Number 17, white holes are a mathematical necessity. A white hole exists on paper before it exists anywhere else. Its birth certificate was signed by Albert Einstein in 1915, even though he never knew it. The odds of a single soldier, Karl Schwarzschild, solving Einstein's incredibly complex field equations just a year later, in 1916, while serving on the Russian front in World War I, were astronomical. He died just months after publishing his solution. That solution, the Schwarzschild metric, was the first exact mathematical description of a black hole. But the math held a secret. The equations describing how space-time curves around a single, non-rotating, uncharged mass were time-symmetric. This means the rules don't care which way time flows. If you film a planet orbiting a star and play the movie backward, it still looks like a valid orbit. The physics works both ways. The Schwarzschild solution described an object that pulls matter in, an eternal black hole. But if you reversed the arrow of time in those same equations, you got something else. You got an object that spews matter out, an eternal white hole. This isn't just a fun thought experiment. It's a direct consequence of the mathematics. The equations don't just allow for a white hole, they demand it as a possibility. The full, complete map of space-time for a black hole, known as the Kruskal-Szekeres coordinate system, shows 4 distinct regions. There's our universe. There's the inside of the black hole, and then there are 2 more regions, a parallel universe and a white hole that ejects matter into that parallel universe. It's not an optional add-on. It's part of the complete package. To accept the math of a simple black hole is to accept the blueprint for a white hole. This creates a serious problem. General relativity is one of the most tested and successful theories in history. It predicts gravitational waves, which we've detected. It predicts the bending of starlight, which we've seen. It predicts the orbital decay of binary pulsars with stunning accuracy, and it predicts black holes, which we have photographed. So if the same theory using the very same equations also predicts white holes, where are they? Their existence is baked into the same mathematical cake as all these other verified phenomena. Physicists can't just ignore them. Like, they have to explain why we don't see these cosmic fountains. The fact that they are a necessary part of the math, but seemingly absent from reality, is one of the deepest tensions in modern physics. It suggests either our understanding of relativity is incomplete, or something is actively preventing white holes from forming or surviving. Number 16, they violate the most fundamental law in physics. The second law of thermodynamics states that the total entropy of an isolated system can only increase over time. And entropy is, simply put, a measure of disorder or randomness. An egg can scramble, but a scrambled egg cannot unscramble itself. A cup of hot coffee cools down to match the room's temperature. The room doesn't spontaneously give its heat back to the coffee. This law is why time seems to have a direction. It's the arrow of time. Black holes obey this law beautifully. In the 1970s, Jacob Bekenstein and Stephen Hawking showed that a black hole has entropy. Its entropy is proportional to the surface area of its event horizon, the point of no return. When you throw something into a black hole, the black hole gets bigger, its surface area increases, and its entropy goes up. The total entropy of the universe increases, and the second law is safe. A white hole does the exact opposite. By definition, a white hole is a time-reversed black hole. If a black hole is a place where entropy increases, a white hole must be a place where entropy decreases. Things would come out of a white hole in a highly ordered state. It would be like a factory running in reverse, taking scrap metal and random parts and spitting out a perfect car. It would be like a fireplace sucking in smoke, ash, and heat and reassembling them into a perfect, unburnt log. This is a catastrophic problem. The second law of thermodynamics isn't just a good idea. It's considered the most fundamental law in physics. Arthur Eddington, a famous astronomer, once said that if your theory is found to be against the second law of thermodynamics, I can give you no hope. There is nothing for it but to collapse in deepest humiliation. A white hole seems to do exactly that. It would be a source of spontaneous order in a universe that relentlessly moves toward disorder. This violation is so profound that it's the #1 reason most physicists believe white holes cannot exist in our universe. For a white hole to form and exist, the universe would have to, at least locally, run backward in time. But that doesn't happen. This suggests that while white holes are valid mathematical solutions, they are not physically realized. Something prevents them from forming. The universe appears to have a built-in censorship against processes that would so flagrantly decrease entropy. A white hole isn't just strange, it's thermodynamically illegal. It breaks the one rule that seems to govern everything, from chemistry to cosmology. Number 15, the Big Bang, was a white hole. The observable universe is about 93 billion light-years in diameter, but it all started from a point of infinite density and temperature 13.8 billion years ago. This initial state, the Big Bang singularity, has no explanation in classical general relativity. The math just breaks down. The origin of the universe is a known unknown. It's a question mark at the very beginning of the timeline. But what if the Big Bang wasn't the beginning? What if it was an event? In the early 2010s, physicists like Hal Haggard and Carlo Rovelli, working with ideas from loop quantum gravity, proposed a compelling theory. The Big Bang wasn't a unique, one-time creation event. It was the explosive eruption of a white hole. The math describing the Big Bang singularity is remarkably similar to the math describing a white hole singularity. Both are points in space-time from which a vast amount of matter and energy emerges. In this model, our universe is the result of a previous universe's collapse. Imagine a universe much like our own, full of stars and galaxies. Over trillions of years, it expands, cools, and eventually collapses back on itself in a big crunch. All the matter and energy rushes together, forming one gigantic black hole that contains the entire universe. But quantum gravity effects, which become important at extremely high densities, would prevent a true singularity from forming. Instead of collapsing to an infinitely dense point, the matter would reach a maximum, but finite, density, the Planck density. At that point, it would bounce. This bounce is the key. The collapse would reverse, and the supermassive universe-sized black hole would transition into a white hole. The explosion of this white hole is what we perceive as the Big Bang. Our universe didn't come from nothing. It came from the remains of a dead universe, reborn through a cosmic rebound. This idea, known as the Big Bounce, solves several problems. It eliminates the need for a singularity at the beginning of time. It provides a physical mechanism for the Big Bang. It suggests a cyclical nature for the cosmos, with universes being born and dying in an eternal cycle. This theory also makes a testable prediction. If the Big Bang was a bounce, it might have left subtle imprints on the cosmic microwave background radiation, the leftover heat from the Big Bang. Scientists are actively looking for these potential signals. The idea that our entire 13.8 billion year old universe, with its trillions of galaxies, is just the temporary exhaust from a single universe-sized white hole is a profound shift in perspective. It turns our origin story from a singular mystery into part of a potentially infinite chain of cosmic events. Number 14, a white hole is a black hole's distant future. Stephen Hawking's discovery of Hawking radiation in 1974 changed everything we thought we knew about black holes. He showed that black holes are not truly black. Due to quantum effects near the event horizon, they slowly leak radiation and lose mass. This process is incredibly slow. A solar mass black hole would take about 10 to the power of 67 years to evaporate. A supermassive black hole at the center of a galaxy could take 10 to the power of 100 years. These are timescales that make the current age of the universe, a mere 13.8 billion years, seem like the blink of an eye. But what happens at the very end of this evaporation? This is one of the biggest unsolved mysteries in physics, tied to the black hole information paradox. When a black hole evaporates, does the information about what fell in get destroyed forever? This would violate a core principle of quantum mechanics. The theory of a black hole to white hole transition, often called the black hole bounce, offers a radical solution. This idea comes primarily from the field of loop quantum gravity, a candidate theory for quantum gravity. According to this theory, gravity itself is quantized, made of discrete units like pixels on a screen. This prevents the formation of a true, infinitely dense singularity at the center of a black hole. Instead, as a black hole collapses, the matter inside gets squeezed to an incredible density, but it never reaches infinity. It hits a fundamental limit, the Planck density. At this point, quantum pressure, a repulsive force predicted by loop quantum gravity, becomes overwhelmingly strong and halts the collapse. The collapsed matter then rebounds outward, but because of the intense time dilation inside a black hole, this bounce is not seen from the outside. From our perspective, the black hole just sits there, slowly evaporating via Hawking radiation. The bounce happens inside, but its effects are trapped behind the event horizon. It's only when the black hole has evaporated down to a very small planetary mass that the event horizon shrinks enough for the effects of the bounce to finally escape. The final stage of the black hole's life would not be a quiet fizzle, it would be an explosion. The black hole, in its last moments, would transform into a white hole and release all the information and matter it ever consumed back into the universe. This event would be fast and violent. This theory elegantly solves the information paradox. Information isn't destroyed, it's just held for an extraordinarily long time and then released. It also explains why we don't see white holes. They are the end state of black holes, and the universe is simply not old enough for this to have happened yet. The first stellar mass black holes are still in their infancy. We are living in the black hole era. The white hole era won't begin for trillions upon trillions of years. We are just too early to the party. Number 13, they are unstable and self-destructive. Even if a white hole could somehow form, it might not last long enough for us to see it. A 1970 paper by Mark Israel and Werner Efron, later expanded upon by others, showed that the concept of an eternal white hole is wildly unstable. The slightest disturbance could cause it to collapse into a black hole. The reasoning is surprisingly simple. A white hole is defined as a region of space-time that nothing can enter. Its event horizon works in reverse. But What happens if a single photon, a single particle of light, tries to approach the white hole? Remember, a white hole is a massive object with intense gravity. That photon would be drawn toward it. As the photon gets closer, it would be extremely blue shifted. Blue shift is the opposite of redshift. It's what happens to light when its source is moving toward you, or when light is climbing out of a strong gravitational field in reverse. In the case of a white hole, the energy of that incoming photon would increase exponentially as it approached the event horizon. A single low-energy photon from the cosmic microwave background could be amplified to have near infinite energy at the white hole's horizon. This massive concentration of energy would instantly have a dramatic effect on spacetime. According to Einstein's E=mc², energy and mass are equivalent. The immense energy of that blue-shifted photon would warp spacetime so severely that it would cause the white hole to collapse. It would essentially wrap a new event horizon around itself, one that pulls things in instead of pushing them out. The white hole would instantly become a black hole. This means that a white hole is its own worst enemy. It cannot exist in a universe that contains anything else. Even the faint afterglow of the Big Bang, the cosmic microwave background radiation that fills all of space, would be enough to destroy any white hole that might exist. And it's like a vampire that is instantly destroyed by the faintest glimmer of sunlight. This inherent instability is another powerful argument against the existence of long-lived white holes. They are mathematical ghosts that are too fragile for the real world. For a white hole to exist, it would need to be in a perfectly empty universe with not a single particle or photon to disturb it. Our universe is far from empty. It's filled with radiation, dust, and gas. So, even if the Big Bang created primordial white holes, they would have been bombarded with particles and collapsed into black holes almost immediately after their formation, long before stars and galaxies ever formed. Number 12, a specific gamma-ray burst, was a white hole. On June 10, 2006, a NASA satellite named SWIFT detected an unusually long and bright gamma-ray burst designated GRB 60614. Gamma-ray bursts, or GRBs, are the most energetic explosions in the universe. They typically last a few seconds and are thought to be caused by the collapse of massive stars, hypernovae, or the merger of two neutron stars. But GRB 60614 was different. It lasted for 102 seconds, and it came from a galaxy with very few massive stars, making a hypernova unlikely. It also lacked a supernova, the bright afterglow that usually accompanies long GRBs. Scientists were baffled. It didn't fit any of the standard models. In 2011, physicists Alon Redder and Shlomo Heller proposed a wild explanation. GRB 60614 was not a dying star. It was the birth of a white hole. They argued that the unique light curve and energy signature of this specific event matched the theoretical predictions of a localized, spontaneous eruption of matter from a white hole. Their theory suggests that tiny primordial white holes might have formed in the very early universe. Unlike the eternal white holes of classical relativity, these would be quantum objects, perhaps connected to the black hole bounce theory. These objects would be incredibly dense and exist in a state of suspended animation for billions of years. Then, due to some quantum trigger, they would suddenly and violently explode. The energy and matter ejected would create a burst of high-energy gamma rays, just like a GRB. The model predicted that such an event would not produce a supernova, and that it would originate from an empty region of space away from active star formation. GRB 60614 fit this description perfectly. This is a highly speculative idea, and the vast majority of astrophysicists still believe there's a more conventional explanation for GRB 60614, even if we haven't found it yet. but it's a tantalizing possibility. It suggests that we may have already seen a white hole and just didn't recognize it. If true, it would mean that white holes are not just a theoretical curiosity, they are real, observable phenomena. The search is on. Astronomers are now re-examining data from other strange, unclassified GRBs to see if they fit the white hole profile. The theory makes specific predictions about the spectrum and polarization of the light from such an event. If another GRB like 60,614 is detected and it matches these predictions, it could provide the first concrete evidence for the existence of white holes. It would be a paradigm shift, proving that these theoretical objects are an active part of our cosmic landscape. And number 11, they are a source of dark matter. About 27% of the universe is made of dark matter. We know it's there because we can see its gravitational effects. It's what holds galaxies together and keeps galaxy clusters from flying apart. But we have no idea what it is. We've never detected a dark matter particle directly. It doesn't interact with light or any other form of electromagnetic radiation. It's a cosmic ghost. The search for the identity of dark matter is one of the biggest efforts in modern science. A theory proposed by Carlo Rovelli and Francesca Vedotto suggests we might be looking in the wrong place. Maybe dark matter isn't a new type of particle at all. Maybe it's the remnants of dead white holes. This idea connects the black hole bounce theory to the dark matter problem. The theory goes like this. In the very early universe, a huge number of tiny primordial black holes could have formed. These would have been much smaller than the stellar mass black holes we see today. Over the age of the universe, these tiny black holes would have reached the end of their evaporation process and transitioned into white holes. But the bounce or explosion of these white holes would be very weak. A very small black hole would transition into a very small, stable white hole remnant. These remnants would be tiny, perhaps with the mass of a grain of salt, but squeezed into a region smaller than a proton. They would be Planck-scale objects. Because they are so small and dense, they would have a very weak interaction with their surroundings. They would have mass and therefore gravity, but they wouldn't interact with light or normal matter in any significant way. They would be, for all intents and purposes, invisible. They would be dark. If the early universe produced enough of these primordial black holes, their white hole remnants could account for all the dark matter we observe today. They would be scattered throughout the universe, forming the gravitational scaffolding for galaxies and clusters, but remaining completely undetected by our instruments. This theory is appealing because it solves two major puzzles at once. It provides a physical mechanism for the end of black hole evaporation, and it provides a candidate for dark matter that doesn't require inventing new particles or new physics beyond quantum gravity. There's even a potential way to test it. While these white hole remnants would be stable for the most part, they could occasionally release bursts of energy. Physicists are looking for faint, high-energy signals from deep space, particularly in the radio or gamma-ray spectrum that have no obvious source. Such a signal could be the smoking gun of a white hole remnant, and the first concrete evidence for this elegant and strange solution to the mystery of dark matter. Number 10. White holes, power-active galactic nuclei. At the center of most large galaxies, including our own Milky Way, lies a supermassive black hole, millions or even billions of times the mass of our sun. In some galaxies, these black holes are actively feeding on surrounding gas and dust. This process creates an active galactic nucleus, or AGN. The most extreme AGNs are called quasars, and they can outshine their entire host galaxy. They are the brightest objects in the universe. The standard model for AGNs is that as matter falls toward the black hole, it forms a spinning superheated accretion disk. Where friction and magnetic fields in this disk generate immense amounts of energy, which is then blasted out into space in the form of powerful jets of radiation and particles. This model works well, but it has some puzzles. For example, it's not entirely clear how the jets are launched with such incredible efficiency and speed. An alternative, though far more exotic, theory suggests that what we see as an AGN is not matter falling into a black hole, but matter being spewed out of a white hole. In this scenario, the object at the galactic center is not a stable, long-lived black hole. Instead, it's a temporally large white hole. This idea, proposed by physicists like Danny Eason and Paul Frampton, links to the concept of a cyclical universe. A supermassive black hole from a previous cosmic cycle could tunnel through the Big Bounce and emerge in our universe as a supermassive white hole. These objects would be unstable and short-lived on a cosmic scale, but their explosive decay could last for millions of years. During this time, the white hole would be constantly ejecting matter and energy that it consumed in the previous universe. This outflow of material would be incredibly powerful and focused, looking very much like the relativistic jets we observe coming from quasars. The white hole itself would be shrouded in a cloud of its own ejecta, making it difficult to observe directly. We would only see the brilliant, energetic fireworks it produces. This theory could explain some of the strange features of quasars, like their rapid variability and the extreme energies of the particles in their jets. It also implies a deep connection between the centers of galaxies and the very origin of our universe. The brightest objects we see in the night sky might not be powered by the death of matter in our own universe, but by the rebirth of matter from a universe that existed before ours. It's a radical departure from mainstream astrophysics, but it shows how the puzzle of white holes can touch upon some of the biggest and most energetic phenomena we observe. Number 9, they are windows to the past. Time travel is a staple of science fiction, but it's a nightmare for physics. The possibility of going back in time and creating a paradox like the infamous grandfather paradox threatens the logical consistency of the universe. General relativity, however, does seem to permit solutions that contain closed time-like curves, which are essentially paths through space-time that lead back to their own past. Or white holes, particularly in the context of wormholes, could be a key ingredient in building such a time machine. The classic wormhole or Einstein-Rosen bridge connects a black hole to a white hole. In its simplest form, it connects two different regions of space-time, or even two different universes. The idea of using this for time travel was explored in detail by physicists like Kip Thorne. The concept works like this. You take a wormhole with two mouths, you leave one mouth stationary, and you take the other one on a journey at near the speed of light, then bring it back. Due to time dilation, less time will have passed for the moving mouth than for the stationary one. For example, the moving mouth might have aged 1 year, while the stationary mouth aged 10 years. Now, if you enter the moving mouth, you will exit the stationary mouth 10 years in its past. You have traveled back in time. The white hole end of the wormhole acts as the exit point, a gateway to a past moment. However, there's a huge catch. All known wormhole solutions require something called exotic matter to keep them open. This is not just matter. That's strange. It's matter with negative energy density. It would have anti-gravitational properties, pushing space-time apart instead of pulling it together. We have never observed such matter, and it's not clear if it can exist. Furthermore, Stephen Hawking proposed the chronology protection conjecture, which suggests that the laws of physics themselves conspire to prevent time travel. He argued that as soon as you tried to create a time machine using a wormhole, quantum fluctuations would build up at the entrance and destroy it in a blast of energy just before it could be used. So, while the mathematics of white holes and wormholes opens a theoretical door to the past, other physical principles seem to slam that door shut. The white hole isn't just a place where matter comes out in this context, it's a place where the past itself could emerge. The fact that the universe seems to forbid this so strongly suggests that the stability and existence of these kinds of white holes are highly unlikely. The universe appears to have a built-in firewall against causal paradoxes, and that firewall might be the very instability of the white holes needed to create them. Number 8. They don't have an event horizon. When we think of a black hole, the most important feature is its event horizon. It's the one-way membrane, the point of no return. Once you cross it, you can never get back out. The physics inside the horizon is cut off from the rest of the universe. A white hole, being the time reverse, is assumed to have a similar boundary, an anti-horizon that you can never enter from the outside. But some theories of quantum gravity suggest that this picture is wrong. The very concept of a sharp, well-defined event horizon might be an illusion of classical physics that disappears when you factor in quantum mechanics. One such idea is the fuzzball theory, which comes from string theory. In fuzzball theory, a black hole isn't a singularity surrounded by empty space. Instead, the entire region inside what we think of as the event horizon is filled with a tangled, vibrating ball of fundamental strings. There is no singularity and no sharp horizon. What we see as a black hole is just the fuzzy quantum surface of this object. If black holes are fuzzballs, what would a white hole be? It would be a time-reversed fuzzball. Instead of absorbing strings that hit its surface, it would be a quantum object that is inherently unstable and radiates strings outward. It wouldn't have a classical, impenetrable anti-horizon. Instead, it would be a messy quantum object that is actively decaying and spewing its constituent parts out into the universe. This perspective changes the nature of a white hole entirely. It's no longer a clean mathematical object from general relativity. It's a chaotic quantum system. This could solve some of the paradoxes associated with classical white holes. For example, the instability problem might be different. A quantum fuzzball might not collapse into a black hole the instant a particle touches it. Its interaction with incoming matter would be a complex quantum process, not a simple classical one. This view also offers a different solution to the information paradox. Information that falls onto a fuzzball, a black hole, gets encoded in the vibrations of the strings on its surface. When the fuzzball decays as a white hole, it releases this information back out. The fuzzball white hole would be a strange object. It wouldn't be a naked singularity, but a massive, extended quantum object with a fuzzy surface that glows with radiated particles and strings. It might not look like a single explosive burst, but a more continuous, albeit violent, outflow of energy. This moves the concept of a white hole away from the abstract realm of space-time geometry and into the tangible, though incredibly complex, world of string theory and quantum information. Number 7, they are the same object as a black hole. This is perhaps the most mind-bending idea. What if a black hole and a white hole are not two separate things, a cause and an effect, a portal in and a portal out? What if they are two different perspectives of the exact same object existing simultaneously? This concept arises from thinking about the experience of an observer falling into a black hole versus an observer watching from a safe distance. For the distant observer, anything that falls into a black hole appears to slow down as it approaches the event horizon, getting redder and dimmer and seeming to freeze in time at the edge forever. From our point of view, nothing ever truly crosses the horizon. For the observer who is actually falling in, however, they pass right through the event horizon without noticing anything special. They continue their journey toward the singularity. Time for them passes differently. Now, let's add in the idea of a black hole to white hole transition, the bounce. From the perspective of the falling observer, they fall in, hit the bouncing core where the singularity would have been, and are then thrown back out. Their personal timeline involves falling in and then being ejected. But what does the distant observer see? They see matter freezing at the horizon of the black hole. And, if a white hole is the end state, they might also see matter being ejected from that same location. The ejection, however, would appear to happen incredibly slowly at first, as the light has to fight the intense gravity. The theory, proposed by Carlo Rovelli and others, is that the infalling matter seen by the distant observer is the outgoing matter. It's not that matter falls in, waits for trillions of years, and then comes out. It's that the event we describe as Matter falling in and the event we would describe as matter being ejected are the same physical phenomenon, just viewed from different reference frames with vastly different flows of time. This is called a Planck star model. From the outside, it looks like a standard black hole, but what we perceive as the event horizon is actually the surface of a super dense object, a Planck star, where time is slowed to an almost complete stop. Matter falling onto this surface is the same matter that is slowly being radiated back out. The black hole and the white hole are not a sequence in time, but two faces of the same coin, one seen from the inside and one from the outside. This is a deep and difficult concept rooted in the way general relativity treats time as a local, malleable thing. It eliminates the need for a singularity and resolves the information paradox in a radical way. Information never gets trapped. It just gets re-emitted over an incredibly long period. The object we call a black hole is, in this view, also a very, very slow white hole. Number 6. White holes must exist to preserve causality. The cosmic censorship hypothesis proposed by physicist Roger Penrose in 1969 is a fundamental yet unproven principle in physics. It comes in two forms, weak and strong. The weak version states that all singularities created by gravitational collapse must be hidden from outside observers behind an event horizon. In simple terms, naked singularities are forbidden. The universe will not allow the creation of a point of infinite density that we can see. The reason this is so important is that a naked singularity would wreck physics. At a singularity, the laws of physics as we know them break down. If we could see one, and if signals could come out of it, then anything could happen. The principle of causality, that an effect cannot come before its cause, could be violated. A naked singularity would be a place from which random, unpredictable information could emerge, destroying the predictive power of science. Black holes respect this principle. Their singularity is safely hidden behind an event horizon. Nothing, not even information about the breakdown of physics, can get out. But what about a classical white hole? A white hole is, by definition, a naked singularity. It is a singularity in the past that is visible to all observers. Matter and energy pour out of it. It's the very thing the cosmic censorship hypothesis is supposed to forbid. So this creates a deep conflict. General relativity allows for white holes. The cosmic censorship hypothesis forbids them. One of them has to be wrong, or at least incomplete. Most physicists bet on cosmic censorship. They believe that some quantum gravity effect or other mechanism prevents naked singularities from forming. This is another way of saying that something prevents white holes from existing. However, some physicists have turned this argument on its head. Perhaps the universe isn't trying to prevent white holes, but is using them in a controlled way. The Big Bang itself was, in essence, a naked singularity that we can all see in our past. So, the universe clearly allows at least one. Maybe the cosmic censorship hypothesis is not an absolute ban, but a rule about how and when singularities can appear. Perhaps the only naked singularity allowed is the one that started everything, the primordial white hole of the Big Bang. All subsequent singularities formed by collapse must be clothed in an event horizon. In this view, the white hole of the Big Bang is special. It's the ultimate cause from which all subsequent chains of cause and effect originate. It's the one time the universe was allowed to be unpredictable, to set its own initial conditions. After that one foundational event, the rules of causality kicked in, and cosmic censorship took over to prevent any further chaos. This would make our universe's origin a unique white hole-driven event, a singular exception to a rule that governs all of cosmic history since. Number 5, they are the source of high-energy cosmic rays. The Earth is constantly being bombarded by cosmic rays. These are not rays of light, but high-energy particles, mostly protons and atomic nuclei, traveling at near the speed of light. Most of them are low energy and come from the sun or supernovae within our galaxy. But occasionally we detect an ultra-high energy cosmic ray, Uhiker, These are single subatomic particles that carry the kinetic energy of a baseball thrown at 100 miles per hour. The origin of these UHECRs is a major mystery in astrophysics. To accelerate a particle to such incredible energies requires an unimaginably powerful cosmic engine. The usual suspects, like supernovae or active galactic nuclei, struggle to explain the highest energies we've observed. The particles are so energetic they shouldn't be able to travel far across the universe without losing energy, yet they seem to come from distant extragalactic sources. In 2014, a paper by Aurelian Barau and Carlo Rovelli suggested a new candidate for the source of these particles, the final explosion of a primordial black hole transitioning into a white hole. The theory builds on the idea that dark matter might be composed of primordial black holes, but it focuses on the very last moment of their existence, when a tiny black hole finally bounces and becomes a white hole. It releases all of its stored mass and energy. This final burst would be incredibly energetic. The theory calculates that the particles ejected from this white hole explosion would have energies right in the range of the observed UHECRs. This theory has several attractive features. First, it provides a specific physical mechanism for producing particles with these extreme energies. Second, because these primordial black holes would make up the dark matter halo of our own galaxy, many of these explosions would be happening relatively nearby. This solves the problem of how the UHECRs can reach us without losing their energy. They don't have to travel across intergalactic space. They could be originating right here in the Milky Way's dark matter halo. The theory also makes a testable prediction. The explosions should be isotropic, meaning they should come from all directions in the sky equally, rather than being concentrated in the plane of the galaxy or from specific sources. This matches the current observational data for UHECRs, which show a surprisingly uniform distribution. If this theory is correct, it would mean that when we detect an ultra-high energy cosmic ray, we are witnessing the death of a black hole and the birth of a white hole. These mysterious particles would be messengers from a quantum gravitational event, providing a direct window into the physics of the black hole bounce. Each ping in our detectors would be the echo of a tiny, ancient black hole finally letting go of its secrets in a final, brilliant flash. Number 4, they are wormholes connecting to our own universe. The classic Einstein-Rosen bridge connects a black hole in one universe to a white hole in a parallel universe. But what if the wormhole connects back to our own universe? This would create an object with very strange properties. Imagine a black hole that is connected via a wormhole to a white hole somewhere else in our same universe. Matter could fall into the black hole in one galaxy and be instantly ejected from the white hole in another galaxy billions of light years away. This object would act as a cosmic shortcut. This is sometimes called an inter-universe wormhole. The existence of such objects would have profound implications. They could explain some astrophysical puzzles, like apparent faster-than-light motion observed in some quasar jets. What we see could be matter taking a shortcut through a wormhole. They could also provide a mechanism for mixing matter across vast cosmic distances, potentially homogenizing the universe in ways we don't expect. A galaxy's worth of material could be siphoned off and deposited somewhere else. However, the physics of such an object would be bizarre. The white hole end would be a fountain of matter that seems to appear from nowhere. So it would not be spewing out primordial matter from the Big Bang, but processed matter from another location in our universe, stars, gas, dust, and anything else that happened to fall into the connected black hole. The chemical composition of the ejected material would be a clue to its origin. Like all wormholes, these would likely require exotic matter with negative energy to remain stable and traversable. Without it, the throat of the wormhole would collapse the instant anything tried to pass through it. There's also the problem of mass. If a black hole is constantly gaining mass from infalling matter, and the white hole is constantly losing mass by ejecting it, how does the system balance? Does the total mass of the wormhole change? The gravitational effects would be complex. From a distance, the black hole mouth would look like a source of gravity, while the white hole mouth would look like a source of anti-gravity, in the sense that it's pushing matter away, though it would still have a positive mass and attract other objects gravitationally. While purely theoretical, the idea of these cosmic transportation tubes highlights the strange possibilities hidden within general relativity. If they exist, white holes might not be relics of the Big Bang or the future of black holes, but active, real-time gateways linking distant corners of our own cosmos in a way that defies our conventional understanding of space and distance. Number 3, they explain the arrow of time. Why does time only flow in one direction? Why do we remember the past but not the future? This is known as the arrow of time. As we've discussed, it's deeply connected to the second law of thermodynamics and the constant increase of entropy. The universe started in a very low entropy state, the highly ordered Big Bang, and has been getting more disordered ever since. But this just pushes the question back. Why did the universe start in such a special low entropy state? Or it's one of the deepest mysteries in cosmology. It's like finding a brand new deck of cards perfectly ordered by suit and number. It's a possible arrangement, but it's an incredibly unlikely one. White holes might provide the answer. In a theory championed by physicists like Julian Barbour, the arrow of time is not fundamental. Instead, it's an emergent property of the universe's structure. The theory suggests that the Big Bang was not a single origin point, but a central point from which two universes expanded in opposite directions of time. Imagine a central moment of perfect chaos and maximum entropy. From this point, the universe evolves in two opposite temporal directions. In one direction, it's our universe, where entropy increases and time flows forward. In the other direction, it's a mirror image anti-universe, where entropy also increases, but their forward is our backward. For anyone living in that universe, their past would be our future, and their future our past. The Big Bang in this view is the common past for both universes. It's a kind of cosmic hourglass with sand flowing out from the center in two directions. What does this have to do with white holes? The Big Bang, the event that sets the low entropy condition for our universe, is mathematically equivalent to a white hole. So this theory is essentially saying that a single primordial white hole is the source of the arrow of time for two universes. It created the special initial conditions that allow for complexity, structure, and the perception of a linear flow of time. Without this specific low entropy starting point, the universe would be a uniform high entropy soup with no structure, no stars, no life, and no perception of time passing. This is a radical idea. It suggests that our entire experience of time, the very fabric of causality that underpins our reality, is a consequence of the unique properties of a white hole that existed at the beginning of everything. It's not that white holes exist within our timeline, it's that our timeline exists because of a white hole. Number 2, white holes are all around us, but they are microscopic. When we think of white holes, we usually imagine massive astronomical objects. But what if they exist on the smallest possible scale? This idea comes from a field of physics that tries to connect gravity with information theory, proposing that space-time itself is built from quantum information. In this model, every particle of matter is a tiny excitation of the underlying quantum space-time. A theory known as spontaneous collapse theory suggests that the wave function of a particle, its cloud of quantum possibilities, can spontaneously collapse into a definite state without needing to be measured. These collapses are random and unpredictable events at the quantum level. Physicist Roger Penrose has suggested that each of these spontaneous collapse events is, in essence, a microscopic white hole. Here's how the logic works. A black hole is a region where gravity becomes so strong that it forces a quantum state to collapse. Information goes in and a definite outcome is forced. Penrose argues that the time reverse of this process must also exist. This would be a spontaneous, uncaused event where a new quantum state erupts into existence. This is a microscopic white hole. In this view, the universe is not a smooth, deterministic machine. It's constantly being pricked by these tiny, spontaneous white hole events. Each event injects a tiny, irreducible element of randomness into the cosmos. This could be the source of all quantum indeterminacy, the reason we can't predict when a radioactive atom will decay or the exact position of an electron is because these events are triggered by the spontaneous eruption of microscopic white holes. This theory also has implications for consciousness. Penrose, along with Stuart Hameroff, has proposed that human consciousness arises from quantum computations happening in microtubules within our brain cells. They argue that our moments of insight, choice, and conscious awareness are linked to these spontaneous collapse events, these microscopic white holes. Our brains, in this view, are acting as amplifiers for the fundamental creative randomness of the universe. This is by far one of the most speculative theories about white holes. It removes them from the realm of astrophysics and places them at the very foundation of quantum mechanics and even biology. It suggests that the same physics that describes exploding galaxies might also describe the firing of a single neuron. White holes wouldn't be distant, rare curiosities. They would be happening constantly, trillions of times a second inside every object, including our own bodies. Number one, you cannot prove a white hole does not exist. This is the ultimate strange truth about white holes. Despite all the powerful arguments against them, their violation of thermodynamics, their instability, the lack of observation, we can't definitively prove they are impossible. The reason for this lies in the limits of our own knowledge. The argument that white holes decrease entropy and violate the second law of thermodynamics is based on classical physics. We don't have a complete, universally accepted theory of quantum gravity. It's possible that in a full theory of quantum gravity, the laws of thermodynamics behave differently under extreme conditions. Perhaps entropy is conserved in some other way that we don't yet understand when a black hole transitions to a white hole. Without that final theory, we can't be 100% certain the second law holds in this exotic regime. The argument that white holes are unstable and would instantly collapse is also based on semi-classical calculations. It doesn't fully account for the quantum nature of the white hole itself. A quantum object like a fuzzball or a Planck star might not be as fragile as its classical counterpart. The instability argument might be a mathematical artifact of an incomplete theory. And the argument from observation, we've never seen one, is the weakest of all. It's an argument from absence. The universe is vast. White hole events could be incredibly rare, or they could look like other things, like gamma ray bursts that we are misinterpreting. Or, as the black hole bounce theory suggests, they might only happen on timescales trillions of times longer than the current age of the universe, meaning none have occurred yet. So we are left in a state of profound uncertainty. Like, white holes are a direct mathematical prediction of our best theory of gravity, but they seem to violate other core principles of physics, the various theories trying to reconcile this lead in wildly different directions. They could be the origin of our universe, the future of black holes, the source of dark matter, the engine of quasars, or even the basis of quantum randomness. The puzzle of the white hole is a perfect reflection of the state of modern physics. It sits at the intersection of general relativity and quantum mechanics, the two pillars of our understanding of the universe. And these two theories give us contradictory answers. To truly know whether white holes exist and what they are, we need to find the deeper theory that unites them. Until then, the white hole remains the ultimate ghost in the machine of physics, a mathematically sound, physically impossible, and endlessly fascinating object that we can't see, can't rule out, and can't stop thinking about. It's a reminder that the map of the universe laid out by our equations may still contain entire continents we have yet to discover.